Now, so let's talk about how you actually get principled components. So you start with a data set. Again, these are my data points. Ignore the colors, ignore the vectors for now. So they're two-dimensional, two attributes, x1 and x2. The first thing that I'm going to do is I'm going to center the data. And centering the data means subtracting the mean, subtracting the average from every attribute so that the origin, the 0, 0, is dead in the center of my data cloud. So once I do that, it's easy to compute the covariance matrix. So let's talk about what the covariance matrix is. The covariance between two attributes is basically an indication of whether they change together or in opposite directions, right? So, for example, the covariance between x1 and x2 is 0.8. So it's a positive covariance. This means that in general, as x1 increases, x2 is going to increase as well. And as x1 decreases, x2 is going to decrease. So you have a positive correlation in the data, right? So, and if it was like that, it would be negative. So that's what the covariance reflects. It reflects the correlation between the different attributes. So how do you compute the covariance? That's the computation, right? You go over the data points. I goes from 1 to n. These are my instances, individual points. I look at the value for attribute A, the value for attribute B in the same instance xi, multiply them together, average out over all data points. Notice I'm not subtracting the mean. Why? Because it's 0, right? I centered the data precisely for that purpose. I want the means to be 0. It just makes the math so much simpler throughout. So that's the covariance. And if you look at this, if you sort of look at each individual data point, that's where the colors comes in. The points that are colored green are the points that contribute positively to the covariance, and the ones that are red contribute negatively to it, right? So in this point, x1 is smaller than the mean, 0. x2 is smaller than mean, so they go in the same direction. One is smaller and another one is smaller. Here, they're both positive. x1 is higher than the mean, x2 is higher than the mean. So all of those points, as x1 moves, x2 moves in the same direction. These points contribute negatively, but overall, as you see, the covariance is positive. So that's the covariance between the two. And then you also have two variances. So 2.0 and 0.6 are just variances along the x1 dimension and x2 dimension in the data. And that defines the covariance matrix. So, great. Now, the covariance matrix is interesting in one aspect. So let's take a vector, really almost any vector in the plane, and I'm going to be working with a red one. So this red one, it has coordinates -1, 1. So that's my vector. Let's take this vector and see what happens when we multiply it by the covariance matrix. So that's my vector, -1, 1. This is my covariance matrix. I multiply them together. I get -2 plus 0.8 minus 1, 1.2, and minus 0.8 plus 0.6 minus 0.2. So that is my new vector. So let's plot that. That's minus 1.2 on the x1, minus 0.2. It's going to point somewhere in there. Okay? Right. Now let's see what happens if we do it again. Multiply it again, we get that. Plot it, that's what it looks like. Multiply it again, we get that. Plot it, that's what it looks like. See what's happening? Multiplying by this covariance matrix seems to take our vector and turn it in a certain direction. But it doesn't just keep spinning, right? It had a pretty big turn, and then a smaller turn, and then a smaller turn. And if we do it a few more times, we're going to get numbers that are bigger and bigger and bigger, right? So I can't draw this anymore. It'd be off the charts. It'd be somewhere in the basement. But if you look at the slopes are actually converging to something, right? So the slope was 0.4 here, 0.45, 0.454, 454, right? So the slope is getting closer and closer to something. And that something, if you look at it, that is the dimension that you would visually pick out as the dimension of the greatest variance in the data, right? That's the dimension where the data points seem to be spread out the most. So you're getting an interesting behavior. When you take a random vector multiplied by the covariance matrix, it turns it towards the dimension of the greatest variance in the data, right? And it will always do that. It won't always go here. So for example, if I picked that vector and started multiplying it, it would actually go there. Right? It would turn in the opposite direction, but always towards the dimension of the greatest variance. So that's kind of interesting. So, and that immediately gives you an idea for how do you extract these dimensions with the greatest spread of the data. Basically, you want to look at the convergence of this. You want to figure out what is the point to which it converges. Or another way to do this is to look for vectors that don't get turned when you multiply them by the covariance matrix. Right? So the vector E2, if I multiply it by the covariance matrix, it's not going to turn. It's just going to get longer. Longer and longer and longer, but it's going to keep pointing in the same direction. So that's what's encoded by this equation. Covariance matrix times a vector is going to be that same vector multiplied by some scalar component. So it's going to get longer, or it might get shorter, but it's not going to change direction. And there's a name for these guys. These guys are actually called the eigenvectors of the matrix that you're multiplying them by. So we're going to have eigenvectors. Each one of them is going to have a corresponding lambda, and that's called an eigenvalue. Right? And for a matrix which is d by d, you're going to have d eigenvalues, d eigenvectors. And these are going to become our principal components. We're going to take the eigenvectors, which have the biggest eigenvalues, and we'll show that they correspond to the dimensions in which the variance is the greatest. Okay.